Some stars die by collapsing into objects so dense that not even light can crawl away. We'll take that journey from a bright, steady star to a compact, mysterious black hole, told simply, with everyday comparisons so it clicks. Think of a star as a giant, simmering pot. When the stove goes out and the lid caves in, things get weird fast, sometimes a gentle sigh, sometimes a kitchen-exploding fireworks show. First, we'll show you the clear steps, how astronomers spot these invisible monsters without seeing them directly, and a few surprising facts that sound like sci-fi but are real. Stick around and you'll understand which stars put on a dramatic exit, which quietly fade, and why your planet is safe enough to keep your houseplants alive. Birth in a cloud of gas and dust. Stars begin life inside vast, cold clouds made mostly of hydrogen gas with tiny solid grains of dust mixed in. Temperatures in these clouds are only a few degrees above absolute zero, so the gas is sluggish and ready to clump together. Even where the cloud is densest, the particles are far thinner than the air in your room. Think of it as a fog so light you could drive a truck through it and not notice, yet spread over many light years it packs enough material to make dozens or even thousands of stars. These patches are often called molecular clouds because the hydrogen exists in paired-up form. The dust grains are just small bits of heavier elements, carbon, silicates and ices, that act like breadcrumbs for future planets. A gentle disturbance can set the collapse in motion. Pressure and gravity are in a quiet tug-of-war, and when gravity wins in a local pocket, that pocket starts pulling in more matter. This is a lot like a tiny bump in a snowdrift turning into a sliding block. Once it starts, it gathers more snow and grows. In space, the kick might come from nearby stellar winds or a passing wave of compressed gas. Turbulence inside the cloud, random motions that stir the gas, help some regions get denser than others, and those denser knots are the seeds of new stars. Multiple seeds often form near one another, which is why many stars are born in clusters or as twins. Fragmentation is nature's way of not putting all the hydrogen in a single basket. As the clump shrinks, it spins faster because of the same principle that makes a figure skater twirl quicker when they pull in their arms. The incoming material flattens into a spinning disk around the central shrinking core. A short sentence. That disk acts like a rotating pancake of gas and dust, and most of the mass flows inward gradually, spiraling like water down a drain. Friction and collisions in the disk heat the gas and produce light at wavelengths our eyes don't see, infrared, instead of bright visible light. Small jets often appear, shooting out along the rotation axis like cosmic garden hoses. These jets help dump excess angular momentum so the central object can keep growing without flying apart. Magnetic fields, which thread the gas like invisible rubber bands, help guide the flow and shape the jets. Material keeps piling onto the central core until the temperature and pressure in its heart become high enough to start sustained nuclear fusion, hydrogen turning into helium, releasing energy that pushes outward against gravity and stabilizes the newborn star. That critical core temperature is extremely high, roughly 10 million degrees Celsius. How massive the initial clump is determines what kind of star forms. Big clumps make bright, short-lived giants, while smaller ones make faint, long-lived red dwarfs. Planets can begin to form in the leftover disk at the same time, sticking together grain by grain in a process similar to how clumps of wet flour form lumps when you knead dough. It's messy, slow, and somehow productive. Every cloud is different in size, density and makeup, so star formation is not a single, neat procedure but a range of outcomes shaped by local conditions. Some clouds give rise to rich stellar nurseries where hundreds of stars are born together, others spawn a lone, shy star. In all cases the story starts with a delicate balance tipped a little too far toward gravity, and then a grand, messy collection of gas and dust does the rest, slow, dramatic and oddly familiar if you think of it as a very long, very cosmic version of building a snowball or letting bread dough rise. The protostar's fiery first act. A protostar begins life when a patch of gas and dust in a cloud is pulled inward by gravity and collapses into a denser lump. As the material falls toward the center it speeds up and piles on, and the motion of that gas turns kinetic energy into heat, kind of like rubbing your hands together when they're cold. Most of the light a protostar gives off at this stage comes from that heat, not from the nuclear burning that powers a mature star. During collapse, the spinning motion of the original cloud becomes more noticeable. Conservation of angular momentum makes the collapsing gas form a flat, rotating disk around the center. Think of a figure skater pulling in their arms and spinning faster, or water spiraling down a drain. Friction and collisions inside that disk also generate heat, and this warm disk feeds material onto the central object. The inflow is messy, clumps, shocks, and shocks again, all acting like a cosmic pressure cooker where heat builds without yet having the stove turned fully on. Powerful streams of gas often blast away from the protostar along its poles. These jets are launched as magnetic fields and rotating gas collaborate to fling material outward, clearing cavities in the surrounding cloud. You can picture magnetic fields as invisible elastic bands threading the gas. When gas moves along them, the bands help sling it out in narrow beams. The outflows serve a practical role. They carry away excess spin and energy so the center can compress further. Without this, venting the system would have trouble shedding angular momentum and finishing the job of forming a real star. From our viewpoint on Earth, these newborn objects usually hide behind thick dust and fog and are best seen in infrared light rather than visible light. Telescopes that detect longer wavelengths reveal warm cocoons and glowing disks, giving astronomers clues about accretion rates and disk structure. In everyday terms, a protostar at this stage is like a campfire being fed with tinder and kindling. It spits and sparks and heats its surroundings, but the full, steady burn of a mature star has not yet begun. And just like splitting kindling to get a balanced flame, the processes of inflow, heating, and outflow must reach the right balance before nuclear fusion finally takes over. Ignition, hydrogen fusion lights the fuse. Deep in a star's core, gravity squeezes hydrogen atoms so tightly that they begin to stick together and become helium, and that sticking releases the heat and light we see. The cores get unbelievably hot, temperatures reach millions of degrees, and the pressure is enormous, which together push positively charged particles close enough to overcome their natural repulsion. Think of it like forcing two stubborn same-poled magnets together. You have to push very hard, and when they finally snap into place, something dramatic happens. Small amounts of mass are turned into energy in the process, which is why a tiny rearrangement of particles lights up an entire star. This chain of reaction starts with protons, which are the tiny positively charged bits inside hydrogen atoms, colliding and joining up to eventually make a helium nucleus. Along the way, fast particles and gamma rays are produced and carry energy outward. That energy gets shuffled through the star, heating gas layers and eventually escaping as sunlight, starlight, and heat. In plain terms, microscopic collisions produce macroscopic warmth. One everyday comparison is a pressure cooker on a stove. Intense pressure and heat change the food inside quickly. In a star, intense pressure and heat change the atoms and create enormous energy instead of a stew. Not every object in space manages to reach these conditions. If a gathering of gas is too small, it can get warm but never hot enough to keep fusion going. Such bodies become brown dwarfs, dim and brooding, like a campfire that never quite caught. Only objects with enough mass squash their cores to the point where sustained hydrogen fusion can begin and keep running. The rule of thumb is simple: more mass means higher core pressure and higher core temperature, and that makes the star more likely to ignite and shine brightly. Stars with less heft burn their fuel slowly and persist for a long time, while massive stars light up fiercely and burn faster. Fusion is immensely efficient compared with ordinary chemical burning. A pinch of fuel being fused in a star gives off vastly more energy than the same pinch burning in a bonfire, which is why the sun can keep Earth cozy for billions of years. The process is self-regulating too. If the core gets a bit hotter, the star expands and cools slightly, and if it cools, gravity squeezes it more and the temperature rises again. That delicate balance between the crush of gravity and the outward push of fusion is what keeps most stars stable for most of their lives. In short, the ignition of hydrogen fusion is the moment a gas ball becomes a true star, and it's both a gentle balancing act and a spectacular energy factory, the universe's ultimate pressure cooker, with a dash of cosmic drama and a wink of humor. Main sequence, life by balance. At the center of a star, tiny hydrogen atoms are constantly joining together to form helium, and that joining releases a tremendous amount of energy as heat and light. This process, called fusion, is what keeps a star shining, simple as that. The energy produced pushes outward like warm breath on a cold window, and that outward push balances the inward pull of gravity trying to collapse the star into itself. Pressure from the hot center and gravity are in a steady tug-of-war. The outward push is not a magical force, it comes from hot gas pressing outward after being energized by fusion. Gravity, meanwhile, is the weight of all that gas pulling everything inward. When those two forces match, the star sits happily in balance. Scientists have a fancy name for this state, hydrostatic equilibrium, but it's easy to think of it as a perfectly balanced seesaw where both sides stay level so no one falls off. How long a star stays in this calm state depends on how much fuel it has and how quickly it uses it. Bigger stars have more fuel but burn it furiously, like a bonfire that roars bright and ends sooner. Smaller stars burn their fuel slowly, more like a candle that lasts and lasts. Our Sun is a middle-sized example. It's steady enough to give Earth a reliable daily dose of light and warmth, which is one reason planets can settle into steady orbits, and why life on one of those planets had a chance to take hold. Everyday comparisons help. A pot on a gas stove will boil fast on high flame and take forever on low, and a star's behavior is similar in principle. Color and brightness give away a star's inner life. Hotter stars glow bluer and are usually more massive, while cooler stars shine with a redder tint and tend to be smaller. You can spot the same idea in a barbecue. The blue part of the flame is hotter than the red embers. Because main sequence stars maintain that internal balance, their light is predictably steady for long stretches, which makes them reliable lamps for surrounding planets and for astronomers trying to read the story written in starlight. In short, the main sequence phase is a long, stable act where fusion and gravity cooperate, mostly without drama, except for the occasional stellar diva that runs out of fuel and ends the show. When fuel runs low, shell burning and expansion. As a star's central fuel begins to dwindle, the cozy balance that held it steady starts to tip. The core, once a busy workshop turning light elements into energy, quiets down and becomes denser and hotter as gravity squeezes it. The fusion doesn't stop everywhere at once, instead it moves outward into a thin shell around the dying core where there's still fuel left, and that shell picks up the work. Think of it like a campfire where the big logs in the center are mostly coal now, while the small twigs around still flare. The overall blaze can even look brighter for a while, but the nature of the fire has changed. Because energy production shifts into a narrow layer rather than being spread evenly through the center, the star's outer skin reacts. The core's squeeze raises the temperature of the shell and boosts how vigorously that shell burns, which pushes more energy outward and makes the outer layers swell. The surface cools at the same time, so the star becomes larger and redder, a gentle giant compared with its former self. A good kitchen example is dough in the oven. The inside gets hotter, gases expand, and the loaf puffs up and browns on the outside. Stars do the same, minus the smell of baking. In more massive stars this shell burning can happen several times with different fuels, producing stacked burning zones like the layers of an onion. Each inner layer burns a heavier ingredient and needs a hotter stove to do it, so the deeper shells run hotter and finish their fuel more quickly. That layered structure can be pictured as a layered cake where each tier is being cooked at a different heat. The top tiers might still be soft while the center is already overcooked. Because the shells are thin and can be unstable, they sometimes flicker or pulse, and those pulses can blow off the star's outer layers into space. That shedding is a bit like an overfilled soufflé that collapses and scatters bits around the kitchen. Observable clues tell astronomers what's happening inside even though they can't open a star like a pot. The star brightens overall, its color shifts toward red, and winds carrying material away strengthen. Telescopes see expanding shells of gas and dust around such aging stars. For sun-like stars this bloating stage will make them enormous compared with their current size, large enough to reach the inner planets and alter their orbits. Mercury and Venus won't escape. Finally, Because heavier fuel stages release less usable energy the deeper you go, there's a point where no further energy-making reactions are possible in the core, and that sets up the dramatic final act. But until that limit is reached, the slow burnout and the handoff to shell burning are the star's last long performance, full of swelling, shedding, and a few theatrical pulses, stellar drama with a dash of cosmic soufflé humor. The fate of low-mass stars, white dwarfs and planetary nebulae. Low-mass stars like the Sun spend most of their lives quietly burning hydrogen in their cores, but eventually that fuel runs out and the core changes its behavior. The outer layers puff up and the star swells into a giant, while the center squeezes hotter and starts burning helium into heavier elements such as carbon and oxygen. The burning moves into shells around the core and becomes unstable, which makes the outer envelope easier to lose. In the end, the star can no longer hold on to those outer layers and they drift away into space, leaving behind the hot, exposed core. That expelled gas lights up because the leftover core is extremely hot and bathed in energetic light. Ultraviolet rays from the hot core knock electrons off atoms in the expanding shell, and when those electrons recombine, the gas glows in visible colors. Different elements show different hues. Hydrogen often gives reddish light, and oxygen can make greenish or bluish tones. The result is a glowing bubble or shell of material called a planetary nebula. Despite the name, they have nothing to do with planets, they simply look round and colorful through small telescopes. Some are nearly spherical, while others are stretched, lobed, or look like cosmic butterflies. Interactions with companion stars, rotation, or magnetic fields sculpt these shapes, much like wind and a fork-shaped pancake batter, into different patterns. The remnant core that remains after the ejection is the white dwarf, and it is essentially the star's leftover engine block. About the size of Earth but holding a mass comparable to the Sun, a white dwarf is incredibly dense. Picture the mass of a full-sized car squeezed into something the size of a sugar cube and you begin to get the idea. Indeed, a tiny spoonful of such material would weigh as much as several tons. It no longer shines by nuclear fusion, instead it radiates stored heat and slowly cools. The pressure that keeps it from collapsing further isn't heat from fusion but a quantum mechanical effect. Electrons are packed so tightly that they resist further squashing, a bit like a crowd packed into an elevator where everyone's pushed up against each other so they can't be compressed more. White dwarfs start out very hot and can shine intensely for a while, but without fusion they fade over extremely long timescales, eventually becoming faint and cold embers, black dwarfs in the far future, though the universe isn't old enough yet for any to exist. If a white dwarf has a companion star, it can steal material and grow heavier. Should it cross a critical tipping point of mass, about 1 4/10 times the Sun's mass, it can no longer remain stable and may explode in a runaway thermonuclear blast called a Type Ia supernova. Thankfully for most white dwarfs the ending is much quieter, they cool and fade slowly, like the embers of a campfire after everyone has gone home. Using the Sun as a nearby example makes this easier to picture. Our star will shed layers and form a colorful shell of gas while its core becomes a white dwarf, a final small, hot ball of carbon and oxygen sitting at the center of a faint nebula. The planets further out will survive in some form, although the inner ones may be seriously scorched or swallowed when the star expands. In everyday terms, the life of a low-mass star is like a theatrical performer who gives a magnificent final curtain call. It throws off a dramatic costume, leaves behind a glowing stage prop, and quietly exits as a compact, dense relic, still fascinating, and with a touch of cosmic drama and humor. Massive stars, bigger, hotter, shorter lives. Massive stars live fast and die young. They burn through their nuclear fuel in a few million to a few tens of millions of years, while a star like our Sun keeps shining for about 10 billion years. This dramatic difference comes down to how much mass a star has. Once a star is roughly 8 times the mass of the Sun or more, its internal pressure and temperature soar and the whole life story speeds up. Brightness scales up too. Some of these giants are thousands to millions of times more luminous than the Sun, so they light up their neighborhoods like a stadium floodlight compared with a household lamp. The reason they burn faster is simple in principle. More mass means stronger gravity squeezing the core, which raises the temperature and pressure until nuclear reactions go much faster. Think of it like a bonfire versus a candle. The bonfire gives off a lot more heat and light but uses up the wood quickly, while the candle can glow for hours. Inside a massive star, hydrogen turns into helium, then helium into heavier and heavier elements in successive stages, and each new stage needs ever higher temperatures. Short, intense phases follow one another, and the star's core works overtime until it can't support itself any longer. When the core finally runs out of the fuel it can use to push back gravity, collapse happens rapidly and often violently. For many massive stars, that collapse produces a supernova, a colossal explosion that briefly outshines entire galaxies and scatters newly forged elements into space. What remains afterward depends largely on the original mass. Leftover cores from the lighter of these giants become neutron stars, while the heaviest collapse into black holes. This threshold behavior around roughly 8 times the Sun's mass is a key rule of thumb for predicting a star's final fate. Massive stars also affect their surroundings while they live. They drive strong winds and intense ultraviolet light that carve bubbles in the gas clouds where they were born, sometimes shutting down nearby star formation and sometimes triggering it in compressed shells. Picture a powerful garden hose that can either water seedlings or blast them away, depending on how you point it. They enrich the cosmos with heavy elements. The oxygen in our lungs and the calcium in our bones were built in stars far more massive than the Sun, so although their lives are short, their legacy is huge. Fusion beyond iron, the energy deadline. In the cores of massive stars, the nuclear reactions that make light into heavier stuff also make the heat and light we see, and that process has a hard stop. Stars combine the centers of atoms, protons and neutrons, to form heavier nuclei, and with most of those combinations the result is a bonus. Some energy is released, like getting free change in a vending machine. That bonus disappears once you reach iron. Fusing iron into anything heavier doesn't give you energy back, it costs you. Think of it as a cosmic vending machine that stops dispensing snacks after a certain coin is inserted. The reason is simple enough without jargon. There is a peak in how tightly the pieces in an atomic center can stick together, and iron sits at or near that peak. For lighter elements, squeezing pieces together makes a more tightly bound center and releases energy. For elements heavier than iron, putting pieces together actually makes the binding looser in terms of energy payback, so you must put energy in instead of getting it out. Picture trying to stack increasingly large, oddly shaped plates. Up to a point they sit snug and stable, and then they become wobbly unless you push them together, which takes effort. Because iron ends the free energy party, the star's central furnace effectively shuts off at that point. Without fresh energy coming from fusion, the pressure that had been holding the core up drops and gravity takes over, collapsing the core inward. Imagine a crowded theater where the people holding up a platform suddenly leave. The platform falls even if the rest of the building is still standing. The collapse can be sudden and violent, and that violence is the engine for the spectacular fireworks that follow. That deadline is also where new kinds of chemistry get their start, but not via the gentle, orderly fusion that built lighter elements. In the collapse and any ensuing explosion, chaotic conditions create the heavy elements by smashing particles together and adding neutrons in rapid succession. You can think of it as a cosmic kitchen blender, nothing pretty, but it mixes raw ingredients into things you couldn't make on the stove. A little dark humor fits. The star runs out of fuel and then throws the ultimate temper tantrum, scattering the heavier elements that will one day become planets, rocks, and maybe even your toaster. Core collapse, the star's last stand. Massive stars run out of fuel in their centers and the gentle balance that held them up suddenly fails. For most of a star's life, heat from fusion pushes outward while gravity pulls inward. When fusion can no longer make energy in the core, gravity wins. The core, now mostly iron, is like the final piece of a jigsaw puzzle that won't fit into a solution. Fusing iron actually uses up energy instead of producing it, so nothing left can stop the squeeze. Pressure that once kept the core from collapsing comes from electrons packed so tightly they resist being pushed together, a quirky quantum effect that behaves like an invisible cushion. This electron pressure can only hold so much weight. If the inner core's mass exceeds a certain limit, known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, that cushion fails. Collapse then accelerates rapidly. The inner core falls inward in a fraction of a second, turning potential energy into extreme heat and density. It's faster than you can blink, and messier than trying to fold a fitted sheet. As the core compresses, strange things happen. High-energy light rays start breaking iron nuclei apart, a process that sucks up energy rather than releasing it, and electrons are grabbed by protons to make neutrons and tiny ghost-like particles called neutrinos. Those neutrinos stream out in huge numbers, carrying away most of the collapse energy, almost like a crowd spilling out of a stadium and taking the warmth with them. In fact, nearly all of the gravitational energy released goes into neutrinos, leaving little left in the matter itself. A stiff, ultradense center forms and slams into the collapsing outer layers, producing a rebound or bounce that launches a shock wave outward. That shock at first seems promising, but it often stalls when it runs into the energy-sapping effects and the heavy infall of outer material. Neutrinos, though barely interacting with matter, can reheat the stalled shock and help revive it. This delicate rescue act is still a topic of active study. Picture a stalled crowd barrier being nudged by a dozen determined ushers. Small pushes can matter when timing is right. The outcome depends on how much mass remains packed into the remnant. If the inner, compact object is supported successfully by the pressure of packed neutrons, a neutron star is born, an incredibly dense city-sized object with gravity and magnetic fields that would ruin your day. If it's too heavy, however, not even neutron pressure can hold it up and the collapse continues to a point where gravity wins completely, forming a black hole. Everyday analogies help. Think of squeezing a snowball until it either becomes a rock-solid lump or crumples into something you can't even recognize anymore. Throughout the collapse, timescales are astonishingly short and temperatures soar to billions of degrees, hotter than the center of most normal stars, creating conditions where matter behaves unlike anything in daily life. Despite the violence, this process seeds the cosmos with new elements and sets the stage for dramatic astronomical fireworks, although the true drama often plays out in invisible neutrinos and the deep physics happening at tiny scales. And, yes, while the core's final moments are brutal, they're also one of nature's most efficient recycling programs, a stellar finale that both destroys and creates. Supernovae, cosmic fireworks and heavy element alchemy. When a very large star runs out of the fuel that keeps its core hot and puffy, gravity suddenly wins and the star can explode in a brilliant flash called a supernova. These explosions can briefly shine so brightly that they rival the light of an entire galaxy, and the blast blows the star's outer layers far into space. You can think of it like a pressure cooker finally releasing everything at once, but on a scale so enormous your kitchen would be jealous. Telescopes pick up the light and the material flying outward, and that light tells astronomers what the explosion threw into space. Inside stars, lighter atoms are fused together to make heavier ones, in a process somewhat like snapping Lego pieces together to build bigger blocks. Hydrogen sticks to hydrogen to make helium, and helium can combine into still heavier pieces, building up elements until the star makes iron at its core. That iron is stubborn. Fusing iron doesn't give back energy the way lighter elements do. Because of that, once a core is packed with iron, the star is in trouble and a collapse or runaway thermonuclear reaction can follow. The explosion itself is where the real heavy lifting happens for the heaviest elements. In the chaos of a supernova, tiny particles called neutrons slam into atomic nuclei so quickly that they build up heavy atoms before anything can fall apart. This rapid assembly creates many of the atoms heavier than iron, things like gold, platinum, and uranium. Not every heavy atom comes from a supernova alone, but these blasts are one of the main factories for such materials. A simple way to picture it, if normal fusion is baking a cake slowly, a supernova is tossing ingredients into a blender at full speed and out comes something you couldn't make in a steady oven. After the blast, millions of tons of new atoms, dust and gas rich in heavy elements, spread into the surrounding space and mix with cold clouds of gas. Those clouds can later collapse to form new stars, planets, and ultimately the raw materials for life. The calcium in your bones, the iron in your blood, and the iodine in your salt were once part of such stardust. So when you use a metal spoon or admire a gold ring, you're holding stuff that was assembled in one of the universe's most violent moments. It's a cosmic recycling program with better flair than your city's pickup truck. Astronomers read the light from supernovae like shopkeepers scan barcodes, identifying elements by their characteristic colors and dark lines. They also study the speed and composition of the ejected material to understand how different explosions build different elements. Sometimes the shock waves from a nearby blast even compress gas clouds and help trigger brand new stars, so a supernova can both end one life and help start many others. Little humor: if the universe had a compost pile, supernovae would be the compost turned with fireworks. Neutrinos, the invisible signal. When a massive star runs out of fuel and its core collapses, the bulk of the collapse energy slips away in the form of neutrinos rather than visible light. These are extremely light, electrically neutral particles that hardly ever interact with ordinary matter. Think of them as the universe's stealth messengers. They pass through entire planets like a breeze through a screen door and carry direct information from the star's deepest interior. Short bursts of these particles are the clearest clues astronomers have about the most violent moments inside a dying star. Neutrinos are produced when protons and electrons in the crushing core are forced together to make neutrons, and that process spits out neutrinos as a byproduct. In plain terms, the star's innards rearrange themselves under intense pressure and release a flood of these tiny particles. Because neutrinos don't get trapped by the dense, chaotic environment the way photons do, they escape almost immediately. That means a neutrino burst reaches detectors long before the explosion's light can push through the surrounding material. Detecting them is a real challenge because of their ghostly behavior. Underground detectors and instruments buried in the Antarctic ice watch for the extremely rare occasions when a neutrino does collide with an atom and produces a faint flash of light. Large tanks of ultrapure water or long strings of light sensors in ice act like enormous, patient pools, waiting for a single, tiny blink. If you like everyday comparisons, it's a bit like standing in a stadium-sized swimming pool and hoping to notice the splash from a single pebble dropped somewhere in the crowd. Humorous, yes, also painfully true. Because neutrinos arrive before most other signals, they serve as an early warning system for astronomical events. Networks of detectors around the world compare tiny differences in arrival times to point telescopes toward the right patch of sky. When a neutrino burst suddenly cuts off, astronomers interpret that abrupt silence as a possible sign that the newly formed core collapsed further into a black hole and trapped outgoing particles. That kind of signature gives scientists a rare, direct window into the moment a stellar remnant crosses the point of no return. Practical applications of neutrino observations extend beyond mere curiosity. They let researchers probe conditions, temperature, density, and the behavior of matter at extreme pressures that light cannot reveal. Ongoing efforts are scaling up detector size and sensitivity, adding new materials and technologies to catch more of those elusive interactions. In short, listening to neutrinos is like tuning into a secret channel that tells the hidden story of a star's death, and the more antennas we build, the clearer that whisper becomes. From core to compact remnant, neutron stars versus black holes. When a massive star runs out of fuel in its core, the center can no longer hold up against gravity and it collapses inward, and what remains depends mainly on how much mass is left in that core after the outer layers are blown away. If the leftover core is not too heavy, neutron degeneracy pressure, a weird but simple idea meaning neutrons are packed so tightly they resist further squashing, can stop the collapse and a neutron star is born. If the core is heavier, nothing can stop the squeeze and a black hole forms, a place where gravity wins so completely that even light cannot climb back out. The dividing line is not a sharp number, but in general cores of roughly 2 to 3 times the Sun's mass tend to become black holes while lighter cores can become neutron stars. A neutron star is a city-sized object with the mass of a star packed into something about 10 kilometers across, so dense that a teaspoon of its material would outweigh a mountain. Picture squeezing a massive cargo ship into a sugar cube, and you have the idea. They often spin very fast because the collapsing core shrinks and conserves angular momentum, like a figure skater pulling in her arms and twirling faster. Some neutron stars sweep beams of radiation across space like cosmic lighthouses. When those beams sweep past Earth we call them pulsars, and astronomers can time their pulses with amazing precision. They also have incredibly strong magnetic fields, a kind of magnet so intense that it would wreck your phone from a great distance, and that field can channel inflowing gas into hot spots that glow brightly in 10th rays. Black holes are simpler to describe and stranger to imagine. They are regions where all the mass is squeezed inside a boundary called the event horizon, and once you cross that boundary there's no return because the escape speed exceeds the speed of light. The center is thought to contain a place where our usual physics breaks down. Around black holes you often see bright disks of gas and dust that heat up as they spiral in, and these glowing disks and jets can outshine entire galaxies in some cases. If you want a life analogy, think of a drain. Stuff spirals inward, heats up, and sometimes a spray shoots out along the rotation axis. Also, for black holes a small increase in mass makes a big difference to how deep the gravity well is, and that is why two similar stars can leave such different remnants. Astronomers tell neutron stars and black holes apart in several practical ways, using light across the spectrum and now even the ripples in spacetime called gravitational waves. A compact object that pulses regularly is almost certainly a neutron star, because the lighthouse beams are a smoking gun. If you see a compact object tugging at a companion star and generating 10th rays without pulses or with very different behavior, you might be looking at a black hole. When two compact objects merge they send out gravitational waves whose shape carries information about whether the partners were neutron stars or black holes. Listening to those signals is like using a cosmic stethoscope. In short, the fate of a stellar core comes down to mass, rotation, and how matter behaves under extreme squeeze, and nature gives us both dense, spinning beacons and mysterious dark wells as end products, two different answers to the question of what happens when a star's heart can no longer resist gravity, and both are stranger than most science fiction. Event horizons, the point of no return. Around a black hole there is a boundary where escape becomes impossible and the usual rules of travel stop working the way they do for us. This invisible edge is what physicists call an event horizon, which simply means the point beyond which nothing can return to the outside world, not even a beam of light. It is not a physical wall you could touch, rather, it is a limit set by gravity and the speed of light, like the last safe step before a waterfall's lip. From a distance you can see effects caused by that boundary, such as gas heating up and brightening, but you cannot see the boundary itself directly with ordinary light. From the viewpoint of someone watching a falling object, things get strange. Clocks and motion near the boundary appear to slow down and the light coming from the object stretches and reddens, fading until it seems to freeze at the edge. For the traveler falling in, however, nothing dramatic necessarily happens at that moment. There is no billboard saying, "No exit." Tidal forces, the difference in gravity between your head and your toes, can become extreme and stretch objects into long, thin shapes if the black hole is small enough, a process often nicknamed spaghettification. Still, for very large black holes those tidal effects near the boundary can be surprisingly gentle at first, so the experience depends a lot on scale. Astronomers don't watch event horizons directly with the naked eye. Instead they infer them from how matter behaves nearby. Fast-spinning disks of gas heat up and glow as they spiral in, and some of that energy escapes in 10th rays and radio waves, while the rest vanishes past the boundary. Telescopes that work together to form a single, enormous eye can even map the dark silhouette where light is swallowed, offering a kind of shadow that tells us a horizon is present. Merging black holes send ripples through space that reveal the nature of their boundaries too, because when two such objects collide the way the newly formed object settles down carries fingerprints of its event horizon. Everyday comparisons help. Think of a one-way turnstile in a subway that lets people enter but not go back, only this turnstile doesn't have a guard and it's governed by the laws of physics. There are still puzzles tied to what really happens to information that crosses the boundary, which keeps physicists talking and joking that the universe has its own cosmic trash can with a surprisingly complicated recycling policy. In practical terms, Event horizons mark the ultimate limit for exploration with light and signals, and they remind us that the cosmos has places where the rules for leaving are simply, and permanently, different. Singularity and spacetime curvature. At the center of a collapsed star, gravity can warp space and time so severely that the usual picture of smooth geometry no longer holds. Spacetime curvature is just a way of saying that mass and energy bend the fabric that tells objects how to move. A simple classroom demo is a heavy ball on a stretched sheet making a dip that causes smaller balls to roll toward it. That sheet picture helps to see why planets orbit and why light bends nearby massive objects, but it leaves out time and can be misleading if pushed too far. A singularity is what the equations of general relativity point to when that bending grows without limit. In plain language, the math starts producing values that blow up, quantities that should describe curvature become infinitely large, and the theory stops giving sensible answers. Picture a calculator trying to divide by zero and returning an error. Physics does something like that. The equations warn that the model has reached its own limits. This doesn't mean there is a tiny, neat ball labeled singularity sitting there like a hidden marble. It means our current rules have run into a situation they cannot handle. One everyday effect that illustrates why things go wrong near a singularity is the tidal force, which is the difference in gravitational pull between two nearby points. Stand on Earth and you don't feel it much, stretch that difference enormously and you would be pulled apart lengthwise and squeezed sideways. Astrophysicists colorfully call this spaghettification. Think of a piece of taffy being stretched at two ends while someone compresses it in the middle. Small differences become huge as curvature increases, and ordinary objects are torn apart because the pull on one side is far stronger than on the other. Paths through curved spacetime, called geodesics, are like the straightest possible routes on a hilly landscape. A car follows the road, a marble follows the dimple in the sheet, and light follows curved paths near massive bodies. This bending of light shows up in astronomy as gravitational lensing, an effect astronomers use to map mass. Different solutions to Einstein's equations produce different singularity shapes. A non-rotating collapse leads to one idealized form, while a rotating solution can produce a ring-shaped singularity. Those are mathematical models, though, and real collapsing stars involve messy physics beyond the neat assumptions in the equations. Because singularities are where curvature becomes extreme and the laws we rely on stop making physical sense, physicists expect that a deeper theory, one that combines gravity with quantum rules, will change the picture. Current research tries to patch or replace the breakdown with new ideas so infinities disappear and the error message goes away. It's like needing a better instruction manual after your old recipe starts instructing you to add infinite sugar. The mystery of singularities isn't just academic, it points directly to the limits of our understanding and to the next breakthroughs waiting to be discovered. Accretion disks, feeding the beast. When matter swirls toward a dense object, it rarely plunges straight in, instead it settles into a flattened, spinning structure that acts like a cosmic dinner plate. This spinning pile of gas and dust heats up as particles rub and crash into each other, and that heat is what makes these disks shine across different kinds of light. The innermost regions, where the motion is fastest and collisions are fiercest, glow with high-energy light that instruments in space can pick up, while the outer bands are cooler and radiate in infrared or visible wavelengths. Friction, think of rubbing your hands together to warm up, is a helpful way to picture what keeps the disk hot. But in space the rubbing is a mix of tiny collisions and more subtle effects. Magnetic fields act like invisible elastic bands connecting different parts of the disk, allowing inner gas to slow down and move inward while outer gas takes up angular momentum and drifts outward. A short way to say this is that the disk has an internal traffic rule that lets material lose its circular motion and fall toward the center. It sounds technical, but the idea is simple. Something has to carry away the spin for matter to get closer to the central object. Daily life analogies work well. A bathtub vortex shows how rotation organizes flow, and a figure skater pulling in their arms speeds up, illustrating how spin and radius interact. A busy roundabout gives another picture. Cars entering and leaving must change speed and position, and some cars effectively get shuffled inward while others move outward. In real accretion disks those cars are atoms and plasma, and the rules include electromagnetic forces rather than traffic laws. Sometimes the process is messy, with clumps and shocks, not unlike flour-forming lumps when you mix batter too fast. Observations back this up. Bright 10th-ray sources in the sky often come from compact objects with feeding disks around them, and astronomers use those signals to learn about conditions near the center. Feeding is not always steady. Disks can flare, dim, or eject part of their material in jets that shoot away at high speeds, which is a dramatic way for the system to shed excess energy and angular momentum. In short, these disks are efficient engines for converting orbital motion into heat and light, and they are central to how black holes and other compact objects grow. It's a messy kitchen but a very effective one, with cosmic snacks getting cooked on a very hot, very fast-moving griddle. Relativistic jets, cosmic particle accelerators. Material falling toward a compact object can be thrown outward in narrow, powerful streams that travel at speeds close to light, and those streams are the workhorses that astronomers call jets. They form when gas and magnetic fields near a dense, spinning object, like a black hole or a neutron star, get twisted and squeezed until some of the material is launched away instead of falling in. Think of the disk of gas as a spinning blender and the magnetic field lines as rubber bands. When the rubber bands snap and twist, they fling bits of soup outward in tight streams. A household example helps. A garden hose with a nozzle produces a focused, fast jet of water instead of a spray. The nozzle is like the magnetic fields that collimate, or narrow, astrophysical jets. Charged particles inside the jets, mostly electrons and protons, ride these magnetic strands and gain enormous energies as they spiral and bump through shocks, which are sudden changes in pressure and speed. This is similar to surfers catching a wave and speeding up, only the surfers are tiny particles and the wave is a shock front in the jet. Astronomers detect the light these particles produce across many wavelengths, from radio waves to 10th rays and sometimes gamma rays, because when charged particles curve in magnetic fields they emit radiation. A simple analogy is how a spinning bicycle wheel can throw off bits of mud in an arc if you spin it fast. Laboratory particle accelerators on Earth, like the large machines people sometimes hear about on the news, speed up particles using electric fields. Cosmic jets do the same job naturally, and often reach particle energies far beyond what we build on the ground, nature's own overachieving accelerator. Jets come in very different sizes and moods. Some are small and fast-changing, tied to stellar mass objects that behave like temperamental teens and flicker on short timescales, while others stretch well beyond their host galaxies and glow steadily, like a lighthouse beam you could read a book by. One famous example visible to many telescopes is the jet coming from a massive galaxy at the center of a cluster. It shows bright knots that look like beads on a string, which mark regions where particles are being re-energized. When a jet points nearly directly at Earth it appears extra bright because of a relativistic effect called beaming. It's like pointing a flashlight straight at someone. Suddenly they notice. Studying jets is practical and lively work for astronomers because jets move energy and matter across huge distances and can shape their surroundings, affecting how stars form or how a galaxy grows. Observations use radio telescopes, optical instruments, 10th-ray telescopes, and specialized techniques that measure polarization, which tells us about the magnetic field direction. Think of polarized sunglasses revealing patterns you otherwise can't see. Researchers also follow how jets change over time to learn about the speed and structure inside them. Small flares can mean a shock passed through, and a new bright knot can mean fresh particle acceleration. In short, these cosmic particle accelerators are messy, powerful, and very effective, like a cosmic espresso machine that keeps scientists jittery with excitement. 10th-ray binaries and microquasars. A pair of stars locked in a tight orbit can become one of the brightest 10th-ray beacons in the sky when one companion pulls gas off the other and onto itself. One of those companions is often a compact object, a neutron star or a black hole, which has strong gravity but very little size compared with a normal star. Matter falling toward the compact object forms a spinning pancake of hot gas called an accretion disk, and that disk gets so hot it glows in 10th rays instead of visible light. These systems are what astronomers call 10th-ray binaries, and they're like cosmic kitchens where one partner keeps stealing the ingredients. As gas from the donor star spirals inward, friction and compression heat it up, much like how stirring batter warms your spoon. The hottest inner parts radiate 10th rays because the particles there have enormous energy. The outer parts emit visible and ultraviolet light, so the system can look different depending on the wavelength you use to observe it. Some 10th ray binaries pulse or blink as the compact object rotates or as blobs of gas pass by, producing patterns that tell astronomers about the size and behavior of the disk and the compact object inside. Think of it as listening for a heartbeat. The timing and rhythm reveal the patient's condition. Some of these systems also launch narrow, fast streams of particles into space, and when that happens they earn the nickname microquasar. Those jets are scaled-down versions of the giant jets seen in quasars, which are powered by supermassive black holes in distant galaxies. Microquasars show similar physics but on a size that fits inside our galaxy. The jets can shine in radio waves and sometimes in 10th rays as particles are accelerated and collide with surrounding material. Picture a garden hose with its nozzle partly pinched. A steady stream becomes a focused spray. Change the pressure and the shape of the stream, and you change how far it reaches. The same idea holds for how the disk and magnetic fields around the compact object control jet formation. Observations often combine 10th ray detectors with radio telescopes to capture both the inflow and the outflow, the disk and the jets, because each tells a different part of the story. Systems such as Cygnus 10th show clear signs that one partner is a black hole because of how the matter behaves under extreme gravity, and other objects like SS 433 reveal spectacular, precessing jets that corkscrew through space. These sources are useful laboratories. They test how matter behaves in strong gravity, how magnetic fields can launch jets, and how energy is converted into particle speed and radiation. And if you want a practical tip, they demonstrate that stealing from your roommate rarely ends well, especially if your roommate is a compact object with an appetite for gas. Detecting black holes, light, motion, and shadows. Stars near an invisible object feel a strong pull, and by watching how those stars move we can weigh the unseen thing. Astronomers track the paths of stars and measure their speeds using the light those stars give off. If a star swings very fast around a tiny corner of sky, something very heavy must be hiding there. This is like tracking leaves whirling around the drain. The tighter and faster the swirl, the stronger the pull at the center. In our own galaxy, a cluster of stars racing on tight orbits points to a compact, massive object at the center, and that motion is one of the clearest fingerprints of a black hole. Hot gas falling toward a black hole lights up and becomes a beacon, and that glow is what many telescopes actually see. Think of a whirlpool of gas heating up as it spirals inward until it shines in 10th rays and visible light. Those are the signals. Because the gas can move at a big fraction of light speed, its light is shifted in color depending on whether it comes toward us or away from us, the same effect that makes a passing ambulance siren change pitch. Astronomers use that color shift to measure speed and direction, and so learn how compact and fierce the invisible engine must be. Bursts of brightness, sudden dimming, and regular flickers all tell stories about how the gas is behaving close to the black hole. Gravity can bend light and turn the sky into a funhouse mirror, and that trick helps reveal hidden mass. When a massive object sits between us and a more distant star, the nearer mass bends the star's light and can make the background star appear brighter or distorted. This is called gravitational lensing, and it works like a cosmic magnifying glass. In practice, astronomers monitor millions of stars and look for brief brightenings that move in ways a normal star would not. An isolated, unseen massive object can be revealed that way. Another technique is to image the silhouette the black hole casts against the glowing gas around it. By linking radio dishes across the globe into a single virtual telescope, scientists can resolve the dark central region, the shadow, and the bright ring encircling it. That dark patch isn't the black hole itself, but rather the absence of light from paths that plunge past the point of no return. Each observational trick complements the others, so no single method stands alone. Motion of stars gives mass and location. Light from hot gas shows energetic behavior and timing. Bending and shadowing reveal geometry and the strong bending of light. Put together, these clues build a convincing case that an invisible, extremely dense object is present. It's a bit like a detective combining footprints, CCTV footage, and a security camera blackout. Piecing all that evidence together leaves very little doubt. And yes, black holes remain poor roommates. They never light up the kitchen, but they sure leave a messy trail of breadcrumbs for astronomers to follow. Gravitational waves, listening to cosmic collisions. Ripples traveling through space carry the signature of the most violent collisions in the universe, and by listening to those ripples scientists can learn about objects that would otherwise be invisible. Think of space as a stretchy fabric. When two massive objects like dense stars or black holes spiral together, they tug and shake that fabric, sending waves outward. Those waves are not sound, but they behave in ways similar to sounds traveling through air. They have rhythm, pitch, and amplitude that tell a story about their source. Detectors on Earth act like enormous ears. Long arms set at right angles use lasers and mirrors to compare tiny changes in length along each direction, and when a wave passes by, the pattern of light changes ever so slightly. Noise is the enemy. Everyday things, traffic, ground motion from waves, even tiny thermal wiggles in atoms, make the instrument jitter, so teams use isolation systems, vacuum tubes, and clever data tricks to separate real cosmic signals from the local racket. Multiple detectors working together make it possible to confirm a true cosmic event and to point roughly where it came from, much like how two ears let you tell which direction a car is honking. The information carried by these ripples is surprisingly rich. The shape of the signal reveals whether the colliding bodies were black holes or neutron stars, and it gives clues about their masses and how fast they were spinning. A short, sharp chirp often signals a black hole merger. A longer, more complex signal can mean two neutron stars dance together for longer before merging, and that kind of event can also fling out matter that later makes light we can see with telescopes. In plain terms, listening to these waves lets astronomers weigh invisible objects and learn how they moved before they merged. It's a bit like identifying a pair of skaters from the sound of their blades on ice. Finding a signal involves pattern matching. Scientists keep a huge library of predicted waveforms, essentially the different songs that various collisions would sing, and they compare incoming data against those templates. If something lines up, alarms go off and the hunt begins. That method is similar to tuning a radio to a weak station or matching a fingerprint at a crime lab. Computational power is essential, because sifting through continuous data to find brief, faint signals is a bit like looking for a whisper in a crowd. Listening to gravitational waves has practical payoffs beyond satisfying curiosity. It complements traditional telescopes and particle detectors, so when a merger makes both waves and light, researchers can combine those clues to build a fuller picture, where the event happened, how much energy was released, and what elements were produced. Everyday analogies help. Hearing thunder and then seeing lightning tells you more about a storm than hearing alone. And yes, sometimes those cosmic collisions are responsible for creating heavy elements that later become things people treasure, like the gold in a ring. Scientists keep improving sensitivity and planning detectors that will listen to different pitches, which will reveal new classes of events. The universe has a lot to say, we're just getting better at eavesdropping. Black hole growth, mergers and accretion. Many black holes bulk up by pulling in nearby gas and dust, which forms a flattened, spinning flow like water circling a drain. This spiraling gas gets squashed and heated as it falls, and the heat makes the inflow glow, sometimes so brightly that the center of a galaxy outshines the rest of the galaxy, and we call it an active galactic nucleus or quasar. Think of the accretion flow as a cosmic blender. Stuff goes in, it gets shredded and lit up, and the black hole quietly fattens while its dinner puts on a light show. The process can be continuous or occur in short, voracious episodes, depending on how much fuel is nearby and how easily it can fall in. Growth by swallowing neighbors is another major route. When galaxies merge, their central black holes are brought close together by gravitational forces, they form a pair, spiral toward each other, and eventually coalesce into a single, larger black hole. The final plunge sends ripples through space, gravitational waves, which detectors here on Earth can pick up, giving us direct proof that black holes do indeed merge. This is a bit like two whirlpools meeting in a bathtub. At first they circle each other, then they join into one stronger swirl, and the splash they make tells you something dramatic just happened. Not every feeding attempt succeeds. As the infalling material heats and radiates, that outward push of light and energetic particles can push gas away, slowing or even stopping further growth. In plain terms, a black hole's appetite can be checked by its own burps. When it eats too fast it shines so brightly that the light blows away the nearby food. A simple life example is trying to stack lightweight napkins while pointing a fan at them. Add too much breeze and the stack falls apart. Astronomers use this balance to understand why some black holes grow rapidly and others stay relatively small even when surrounded by gas. The environment makes a big difference. Gas-rich galaxies, where cold clouds of material are abundant, tend to feed their central black holes more efficiently. In gas-poor galaxies, mergers become the dominant growth channel. The black hole gains mass mainly by swallowing other black holes rather than by steady feeding. Picture a city with plenty of grocery stores versus one that survives by annexing neighboring towns. One feeds itself, the other grows by mergers. Sometimes mergers also kick the newly formed black hole. Asymmetric emission of gravitational waves can give a recoil that sends the remnant careening through its host, possibly displacing it for a while. Accretion can also produce powerful, narrow jets that shoot material far from the center, and those jets can change the galactic neighborhood by heating or clearing gas, which then affects future feeding. So a black hole doesn't only passively gain mass, it can actively regulate its supply. That feedback is a bit like a mischievous chef who, after eating too much, stomps on the pantry and locks the door so nobody else can snack. Disruptive and effective. Observations across the electromagnetic spectrum and gravitational wave astronomy together give a fuller picture of these growth channels. Bright accreting black holes reveal themselves in 10th rays, optical light, and radio waves, while merging black holes announce themselves through spacetime ripples. Combining these signals is like listening and watching at the same time. You get to see both the messy dinner and the loud collision afterward. And yes, while the details can be deeply technical, the big takeaway is simple: black holes grow by eating and by merging, sometimes politely and slowly, often ravenously, and occasionally with a dramatic cosmic kick that would make even the rowdiest diner blush. Black hole demographics: counting the darkness. Astronomers divide these dark objects into families based on how heavy they are and where they live, and that gives the first handle on counting them. Stellar black holes come from dead stars and weigh a few times as much as the Sun, while the giants at galaxy centers, called supermassive black holes, outweigh the Sun by factors of millions to billions. Something in between, the intermediate kinds, is harder to pin down. Think of it like sorting rocks on a beach: pebbles, boulders, and those mysterious lumps you trip over that are somewhere in the middle. This mass-based grouping helps guide which tools scientists use to find each kind. Astronomers don't count black holes by looking for light from the holes themselves, because they emit none. Instead they watch for telltale effects on nearby matter and space. When a black hole pulls gas from a companion star, the gas heats up and shines in 10th rays, making the system stand out in 10th ray surveys, like seeing steam and guessing there's a hot kettle. Other times researchers track the motion of stars or gas near a galaxy's center. Rapid orbits betray an invisible heavyweight. Mergers between black holes produce ripples in spacetime that gravitational wave detectors pick up, and that method has opened a brand new window on the populations of stellar mass objects. Occasionally a black hole bends light from a background star enough to make the star brighten briefly, which is a very subtle way to reveal an otherwise invisible body. Counting them accurately requires careful accounting for what we can and cannot see. Bright, feeding black holes are easy to spot, but most are quiet and invisible, so raw detection numbers undercount the true population. Scientists use models to correct for that, much like an ecologist estimates hidden animals from tracks. Detection methods also favor certain masses and environments. Gravitational wave detectors are tuned to merging stellar mass pairs, while radio imaging picks out the most active supermassive centers, so different surveys must be combined to get a fuller census. Selection effects are a headache, but they're predictable if you know how your instruments hunt, and correcting for them is a big part of demographic work. Knowing how many black holes of each type exist and where they live answers big questions about how stars and galaxies evolve. The relative abundance of small versus large black holes tells whether most black holes grow by swallowing gas, eating stars, or merging with other black holes, and that shapes models of galaxy growth. Ongoing and upcoming surveys, with better sensitivity and wider coverage, will reveal quieter and rarer members of the population, gradually filling in the blanks, like hiring more detectives to solve a long-running mystery. It's a slow, careful business, but every new detection sharpens the picture and often brings a surprising hint, which keeps even the most buttoned-up astronomers grinning behind their coffee cups. Supermassive black holes, hearts of galaxies. At the center of nearly every large galaxy sits an object so massive that its gravity controls the motions of stars and gas near it. In our own galaxy, that central object, known by a special name, contains about 4 million times the mass of the Sun. Other galaxies can have much bigger centers, with masses that are measured in billions of suns. One famously photographed by a global network of telescopes turned a fuzzy patch of light into a shadowy ring that confirmed theories about how these objects bend light. These giants are not planets or burning balls of gas. They are extremely compact concentrations of mass with gravity so strong that, past a certain point, nothing can escape. The point of no return around them is small compared with the whole galaxy but decisive for anything that gets too close. Picture a bathtub drain. Water far away keeps circling the basin, but anything that reaches the whirlpool center gets pulled down. That whirlpool is like the boundary around a black hole, though the real physics is stranger and more extreme. Matter falling in usually forms a flat, glowing disk as it spirals toward the center, and that disk can heat up and shine brighter than the rest of the galaxy. In simple terms, rubbing and squeezing gas and dust together turns gravitational energy into light, much like squeezing a spring and making it release energy. Some of that energy shoots out along the poles in narrow, fast streams known as jets. If you want a household comparison, think of a garden hose spraying off-center while a blender at the nearby kitchen counter spins a mess of ingredients, messy, noisy, and powerful, but it also mixes things in useful ways. Astronomers find and study these central masses in several practical ways. Tracking stars as they zip around the center reveals how heavy the hidden object must be. Bright disks and jets glow across radio and 10th-ray light, which ground and space telescopes can pick up. And when networks of telescopes work together, they can resolve the shadow cast against the glowing disk, giving a direct look at how light behaves near that compact mass. These methods have shown that such central engines are common and that their activity can shape a galaxy's life by stirring gas, slowing or speeding the birth of new stars, and redistributing matter. Despite being called black holes, they do not act like cosmic vacuum cleaners sweeping up everything in sight. Most of a galaxy's stars orbit far outside the reach of the center's swallowing region. A massive black object can weigh as much as billions of suns and still fit into a volume no larger than a small, dense city by galactic standards. So while they are the dynamic, sometimes dramatic hearts of galaxies, they are also odd neighbors, incredibly heavy, surprisingly compact, and a constant source of both mystery and spectacular light shows. Tidal disruption events. Stars torn apart. A star that drifts too close to a massive black hole is pulled apart by gravity differences across its body, a process much like stretching taffy until it snaps. This happens because the side of the star nearer the black hole feels a stronger pull than the far side, overwhelming the star's own gravity that normally keeps it together. The point where this tear begins is often described as a simple boundary. The star crosses it and the black hole's pull wins, but you can think of it as the moment your dough pulls into long strands instead of staying a ball. Small examples from everyday life help. Ocean tides are caused by the moon's gravity tugging more on one side of Earth than the other, and that same idea on steroids is what rips the star apart. When the star is stretched into a long stream, part of the shredded material flies outward and part falls back toward the black hole. Some of the returning debris settles into a hot, spinning disk that glows very brightly. That glow can be seen in ultraviolet, 10th ray, and optical light, depending on how the material heats up and how the system is oriented toward us. Sometimes the inflow launches narrow, fast jets of particles that shine especially brightly in 10th rays and radio. Spectra of the light, basically the color fingerprint, often show very broad emission lines from hydrogen or helium, indicating gas moving at thousands of kilometers per second, and the brightness typically rises and then fades over weeks to months or even longer. Astronomers spot these events using wide-field optical surveys that watch millions of galaxies and space telescopes that catch ultraviolet and 10th-ray outbursts. Follow-up radio observations can reveal any jets. Detecting one is like hearing a distant firework in a noisy city. Surveys find the flash, then other instruments rush in to figure out what kind of blast it was. Piecing together data from different wavelengths gives a much clearer picture, because each band of light comes from a different part of the wreckage. The hottest inner regions glow in 10th rays, while expanding debris and shocks light up in optical and radio. Tidal disruptions are more than dramatic showpieces, they are practical tools for science. They let astronomers find black holes that were otherwise quiet, measure black hole masses and spins by modeling how material falls in, and probe the internal structure of stars by the way the debris is distributed, like learning about a cookie by studying the crumbs. And yes, there's a bit of cosmic schadenfreude. Watching a star get shredded is how we learn how gravity behaves in extreme conditions. A touch of humor helps. After all, it's the universe's worst breakup turned into a laboratory, but the data yields serious insights into how black holes eat and how matter behaves under crushing forces. Time dilation and strange relativistic effects. Clocks that move quickly or sit deep in a gravity well simply do not agree with clocks far away. That is a straightforward result of relativity and has real-world consequences. When something moves near the speed of light, time measured on that moving object's clock runs slower compared with a stationary observer. This is called velocity time dilation, but think of it simply as fast travel, slow clock. A clear, tested example comes from muons, tiny particles created high in Earth's atmosphere. They live just a short while in their own frame, yet because they streak toward the ground extremely fast, many survive long enough to reach detectors at the surface. Particle accelerators also rely on the same effect to keep beams behaving as expected, so this isn't just a laboratory curiosity. Gravity does the same kind of clock warping, but via mass instead of speed. Clocks closer to a massive object tick more slowly compared with clocks farther away. This is gravitational time dilation. The Global Positioning System uses this fact every day. Atomic clocks on GPS satellites experience both the slowdown from their orbital speed and a speed-up because Earth's gravity is weaker up there. Engineers must correct both effects or consumer navigation would drift and your phone would happily send you to the wrong coffee shop. So relativity isn't optional. GPS shows it is practical. Near a black hole, these effects become extreme and strangely visible to outside observers. Someone falling toward a black hole crosses the horizon without feeling a sudden clock freeze, their own watch ticks normally. From afar, however, that same person seems to slow down as they approach the horizon and their light becomes stretched to longer, redder wavelengths until it fades away. That stretching of light is known as gravitational redshift. Light climbing out of a deep gravity well loses energy and shifts toward the red end of the spectrum. It's a bit like watching a car drive into thick fog. Its taillights dim and seem further away, except with a physics twist rather than bad weather. Relativity also scrambles the idea that two separated events happen at the same time for everyone. Observers moving relative to one another can disagree on whether events were simultaneous. A simple way to think about this is, two flashes that look simultaneous to a person standing still may not appear so to someone zipping past. This relativity of simultaneity matters for synchronizing clocks across networks and satellites. Engineers take it into account so transactions and signals stay coordinated. There is another practical rule tied to all this: nothing can travel faster than light, which protects cause and effect. In plain terms, you can't send a message that makes someone react before the message is sent, so no time travel texting to skip Mondays. Measurements depend on perspective. The time recorded by a clock traveling with an object, its proper time, is what that object experiences directly, whereas coordinate time is what a distant observer might use to describe many events together. Experiments with atomic clocks flown on aircraft and in labs, and observations of particles from cosmic rays, repeatedly confirm these differences in real setups. So when you hear about clocks slowing near a black hole, or muons living longer because they zoom toward Earth, it's not sci-fi, it's the same physics that keeps your navigation app honest and particle physics experiments predictable. And as a bonus of cosmic irony, if someone falls into a black hole, onlookers may get stuck watching them take forever to arrive, like a very slow, very tragic parking maneuver. Hawking radiation and quantum mysteries. Near a black hole's edge, empty space isn't so empty. Tiny pairs of particles and antiparticles constantly blink into being and then annihilate each other, a jittery feature of quantum mechanics that we call vacuum fluctuations. Think of it like steam forming on a hot pan, little bubbles appear and vanish, but near the black hole's boundary one of those bubbles can behave differently. If one member of a pair falls over the edge while the other escapes, the escaping particle can be detected far away as a faint glow, a leak of energy that slowly shrinks the black hole. It's a strange process, and the simplest way to picture it is to imagine a cosmic kettle that is slowly steaming away. That outgoing glow has a special character, it looks thermal, much like the warmth you feel from a radiator or the red glow from a hot stove. But for real, everyday black holes, the ones formed by collapsed stars, this thermal emission is unbelievably weak, far weaker than the light and heat coming from the surrounding space. Put another way, a small candle gives off more detectable warmth than these objects do. The black hole's whisper is buried beneath louder cosmic noises. Only if a black hole were extremely tiny would this radiation become strong enough to be obvious, which is why it's so hard to spot directly in the night sky. A thorny question follows from that tiny glow. Quantum rules insist that information about a physical system can't simply vanish, but a classical black hole seems to swallow everything and hide the details forever. This clash is called the information paradox. A helpful everyday comparison is a shredded recipe card versus a burned book. When you shred paper, you can in principle piece the recipe back together. When you burn it, the ingredients are scattered into smoke and heat, but, in theory, the underlying physics still contains the information. A black hole looks like the ultimate burn pile. Where did the recipe go? Some ideas suggest the escaping radiation subtly carries the information out, encoded in correlations like secret Morse code hidden in the steam. Another idea says that the information is smeared across the black hole's surface, as if a beach encoded a message in the pattern of sand grains. None of these ideas are simple, and they spark lively debates among theorists. Laboratory analogs have helped bring these abstract ideas into practical view. Experiments with flowing water, optical fibers, and other trick setups can mimic the conditions near a horizon well enough to show related effects, and these tabletop versions have produced signals that behave like the predicted radiation. Such experiments don't prove every detail of theory, but they give confidence that the basic concept is sound and that quantum fields behave strangely when horizons are involved. The whole topic sits at the intersection of two great theories, the microscopic rules of quantum physics and the geometric stage of gravity, and resolving the puzzles here could change how we understand the universe. In short, black holes may be less like bottomless trash bins and more like mysterious safes whose combination we haven't quite learned. Until then they keep whispering their secrets in a language only the quantum world fully understands, and that is both maddening and kind of delightful. The information paradox simplified. A black hole has an outer boundary called the event horizon, and once something crosses that line it cannot come back out. Radiation can be emitted from the region around a black hole in a way that looks like ordinary thermal heat, and if that process continues the hole can slowly lose mass and vanish. That setup creates a blunt clash. The usual rules of quantum physics say the full description of a system never truly disappears, but the simple picture of a black hole evaporating seems to erase the detailed information about what fell in. Think of information as the full recipe for a dish rather than just a smell. Toss a cookbook into a bonfire and the paper turns to ash and smoke. To a casual observer the original recipes seem lost. Short sentence for effect. In fundamental physics, however, the rules are more like a kitchen camera that, in principle, can reconstruct the cookbook from the motion and heat of the flames. The worry with black holes is that the outgoing radiation looks random, like steam rising from the fire with no clear link back to the original pages, so when the fire goes out there is nothing left that obviously contains the recipes. Several simple ways to think about possible solutions have been proposed. One idea says the radiation is not truly featureless. Tiny, subtle correlations in the emitted particles could secretly carry the recipe information out, scrambled but recoverable if you could see everything very precisely, like a shredded letter that, with patience, can be taped back together. Another idea treats the black hole surface as a kind of storage medium, information about what fell and gets written, in a scrambled form, onto the boundary so that the outside world can, in principle, read it back. Picture a thin wallpaper that somehow encodes the entire contents of a room. Some suggest a small leftover object could remain after evaporation and keep the missing data safe, similar to hiding a tiny USB stick in a supposedly empty vault. There are also more dramatic proposals where the boundary becomes violently energetic and would destroy anything trying to pass through, an unpleasant welcome mat for infalling matter, though that notion is controversial and hard to reconcile with other parts of physics. Why should any of this matter beyond fascinating thought experiments? Because the question touches the core principle that causes and effects in quantum theory are reversible in principle. Losing information would force a major rewrite of those rules. In everyday terms, it would be like your bank insisting that account records simply vanish sometimes, making reliable prediction impossible. Many researchers lean toward the view that information is ultimately preserved, and ideas about subtle correlations and surface encoding are encouraging because they keep the main rules intact. Directly testing these thoughts is extremely difficult, the signal involved is faint and subtle, so for now much of the evidence is theoretical and based on consistency checks. Practical consequences reach into how we try to combine gravity with the rest of physics, and that makes the paradox a central puzzle rather than a niche complaint. For the curious mind, it's a rare moment where a simple-sounding question, what happens to the bookkeeping of the universe, forces us to rethink the basics. And if you ever misplace your keys, take comfort, at least in ordinary life lost information usually turns up under the couch, not hidden in the event horizon of a cosmic vacuum cleaner. Simulations and virtual black holes. Scientists recreate the death throes of massive stars on supercomputers by turning physics into instructions a machine can follow, and these simulated collapses let researchers watch black hole birth without leaving Earth. To do that, they solve equations that describe how space, time, energy, and matter interact, but the computer version breaks space into many small boxes and updates what happens in each box step by step. That approach is similar to how weather models forecast rain by dividing the sky into a grid, except here the rules must handle extreme gravity, hot plasma, magnetic fields, and particles like neutrinos that stream out of the collapsing star. These calculations rely on specialized numerical tools and huge computing power. Some software packages are openly shared among researchers so teams can build on each other's work. Supercomputers and graphics processors, GPUs, crunch the heavy math. Think of it like rendering a blockbuster movie scene, but instead of making an alien look real, the goal is to predict how light, gas, and gravity behave when a star implodes. The computer spends days or weeks on a problem that a casual gamer's PC might take years to attempt. Simpler physics engines used in video games give plausible motion for fun, while astrophysical simulations chase precision down to tiny details. Visualization turns raw numbers into pictures and even virtual reality experiences that reveal how a black hole would bend light and swirl gas. Scientists use ray tracing techniques, following virtual beams of light through warped space, to show the distorted appearance of an accretion disk, producing a shadow and bright rings much like a funhouse mirror warps your reflection. Observations from radio telescopes are compared with these simulated images so astronomers can test whether their models match reality. Meanwhile, interactive planetarium shows and VR demos let the public and students explore these scenes. The visuals are not just pretty, they are diagnostic tools. Laboratory analogs provide another route. Researchers make systems that mimic certain behaviors of real black holes so they can experiment in a tabletop setting. For example, fluid vortices can trap surface waves in a way that loosely resembles how an event horizon traps light, and carefully controlled optical systems or ultra-cold atomic gases can create conditions where wave behavior imitates processes predicted near horizons. These are not tiny black holes eating lab equipment, of course, but they help scientists test ideas about wave emission and horizon effects in a controlled way, like practicing a complex dance routine on a small stage before performing in a stadium. All of this improves understanding in practical ways. Simulations predict the signals telescopes and gravitational wave detectors should see, which helps observers know where to look and what patterns to trust. They also expose the limits of current theory by showing where approximations break down and where more physics needs to be added. Progress is steady and collaborative, and though computers are powerful, they still rely on good input physics and clever algorithms. In short, virtual black holes are a combination of high-end number crunching, clever lab tricks, and visual storytelling that together make an invisible and extreme process into something understandable, and occasionally, entertainingly strange. Black holes in popular culture and myth. Many people picture these objects as cosmic vacuum cleaners that rip stars apart, and that image sticks because it is dramatic and easy to grasp. In plain language, a black hole is a place in space where gravity is so strong that light can't get out, so it looks like a dark patch against the stars. Think of it as a very deep well in the fabric of space where anything falling in doesn't come back. Everyday comparisons help: a drain in a bathtub, a whirlpool in a river, or a very powerful magnet for matter, but beware, nothing like an actual bathtub will appear in space. These vivid, simple metaphors are why black holes have slotted so neatly into myths and popular stories. Stories have always needed something ominous to stand for the unknown, and black holes perform that role brilliantly in modern myth-making. Tales of swallowing beasts or bottomless pits from older folklore map easily onto the idea of an invisible, consuming force in the sky, so contemporary storytellers borrow that sense of dread. People turn the concept into moral or emotional metaphors too: a black hole of grief, or a career black hole, and those everyday phrases show how mythic language migrates into daily speech. Humor sneaks in often. Comedians joke about losing socks to the laundry as if there were a tiny domestic black hole behind the dryer. Films, television, books, and games use black holes as plot engines because they are both scientifically intriguing and narratively flexible. Some stories show them as perilous traps that destroy what falls inside, others as gateways to other regions of space or alternate realities. A handful of well-known movies literally place characters near one to explore what happens when gravity behaves strangely, while science fiction TV episodes frequently use black holes to create dramatic tension or to explain mysterious disappearances. Video games and comic books often amplify the visual and emotional aspects, turning the black hole into a visual spectacle and a convenient shorthand for ultimate danger or cosmic mystery. Popular portrayals sometimes get the science right, and sometimes they stretch it for effect. The basic idea, strong gravity, no light escaping, is usually accurate, and creative works often borrow real phenomena like the way objects stretch under intense gravity, which can be likened to pulling taffy. But many stories depict people surviving a close pass, or using black holes as neat wormholes to elsewhere with no consequences. That makes for exciting drama, though in reality the effects near a black hole would be extreme and not movie-friendly. Educators and planetariums often use film clips and literary references as teaching moments to correct misconceptions while keeping the public engaged. Artists, musicians, and writers keep reinventing the symbol. Visual artists treat the black hole as a dramatic absence of light to explore themes of loss, mystery, and transformation, while songwriters use it as shorthand for obsession or disappearance. In everyday life, journalists, economists, and ordinary people borrow the term to describe anything that seems to consume resources with no visible return, which shows how scientific concepts become cultural tools. The mix of awe, fear, metaphor, and a touch of joking, like blaming a missing car key on the nearest domestic singularity, keeps black holes both frightening and familiar in the popular imagination. Future telescopes and unsolved questions. Some new observatories will look in kinds of light our eyes never notice, like infrared and 10th rays, and that lets astronomers see through clouds of dust to the hot, hidden hearts of dying stars. Ground telescopes with huge mirrors collect many more photons, which is like using a bigger bucket to catch more rain so faint flashes don't slip by. Space telescopes avoid the blur of Earth's air, and when you combine many radio dishes spread around the planet, you can make images with the sharpness of a continent-sized eye. That trick already gave us the first silhouette of a black hole and will get even better. Engineers are building instruments that act like very fancy sunglasses for telescopes. Coronagraphs and starshades block the glare of a bright star so a faint companion can be seen, much as shading your eyes with a hand helps you spot a bird by a lamp. Adaptive optics are tiny, fast mirrors that correct the twinkle from our atmosphere in real time. Smartphone camera stabilization is the household cousin to this technology. These tools are practical. They help trace the faint gas around a collapsing star and let us watch how material swirls before being swallowed by a black hole. Big unsolved questions drive these projects. We still do not know all the steps that decide whether a massive star ends its life as a dense neutron star or collapses into a black hole, and why some explosions fling material in one direction while others are messy. Another puzzle is whether a middle-sized class of black holes exists, those that would be heavier than the ones formed from single stars but lighter than the monsters at galaxy centers. Finding solid examples would fill an obvious gap, like discovering a missing rung on a ladder. Telescopes across the spectrum tackle different parts of the problem. 10th-ray instruments reveal the hot inner flow near a black hole where gas reaches temperatures hotter than the surface of a kitchen oven by many orders of magnitude. Radio arrays map jets that shoot out at nearly the speed of light. Infrared cameras see through dust to newborn stars and the remains of explosions. Surveys that cover large swaths of sky will catch rare events, for instance, when a star wanders too close and gets torn apart, giving statistical samples instead of lucky anecdotes. Complementary techniques are also coming into their own. Gravitational wave observatories listen for the ripples in space itself when compact objects collide, and future space-based detectors will tune into lower-pitched mergers that ground instruments can't hear. Combining those sounds with electromagnetic images, light of all colors, gives a fuller story, like watching a movie while also hearing the soundtrack. This multi-messenger approach can reveal how fast black holes spin, how mass is exchanged in binary systems, and even test whether extreme gravity behaves exactly as our current theories predict. Even with better eyes and ears, surprises are likely. Instruments being tested now will let astronomers make time-lapse movies of gas orbiting close to an event horizon, and that could highlight behavior we didn't expect, forcing theory to catch up. The next generation of telescopes and detectors therefore feel like new senses for humanity, awkward at first, then indispensable, and occasionally very good at ruining our smug assumptions about how simple the universe was. If Earth met a black hole, scenarios and myths. A black hole is not a giant space vacuum that sucks everything in like a cosmic Roomba. It is simply a region where mass is packed so tightly that its gravity becomes extremely strong near it. Far away, the pull from a black hole follows the same rules as any other mass. If you stand twice as far, the pull gets much weaker. Think of it like a very heavy bowling ball. If you make that ball small enough, it becomes denser, but a bowling ball's pull on nearby toys doesn't suddenly reach across the room. If a black hole passed through the outskirts of the solar system at a great distance, the effect on Earth would likely be negligible. Satellites and planets feel gravity from whatever mass is nearby, not from how compact that mass is. Replace a familiar heavy object with an equally heavy but smaller one, and the motion of a tennis ball around it won't change, the paths stay the same unless you move closer. So a distant black hole behaves, for orbital mechanics, like any other distant mass. A closer encounter changes the story. Strong differences in gravity across Earth, stronger on the side nearer to the black hole and weaker on the far side, would begin to stretch the planet. That stretching is called tidal force, and you can see a mild version of it every day. The moon pulls on Earth and makes tides. If a black hole came within a few times Earth's distance, those tidal forces could first wrench oceans into unusual tides, then strain the crust, and eventually pull rocks apart. Small things would be lifted and flung, and larger structures could fracture. Picture a big bathtub drain slowly deforming the water surface, only the water is the solid ground and the drain is gravity getting meaner the closer you get. A direct, very close passage would be catastrophic for the planet itself. Under extreme tidal forces, Earth would be stretched into a long stream of debris that could either spin away, form a ring, or be swallowed bit by bit. That horror movie image of Earth neatly sucked whole in an instant is wrong. The process is messy and violent, more like dough pulled into strings than a tidy ingestion. In such an event, heat and friction would vaporize materials, creating a hot, glowing cloud that might light up the surrounding space, much like when metal gets white-hot in a forge. Some popular myths deserve a quick burial. One is that a small black hole passing through Earth would leave an invisible tunnel in its wake. In reality, a very tiny, fast-moving compact object would interact strongly with matter along its path, producing shock and heat. It wouldn't create a neat hole you could drop a marble into. Another myth claims black holes are literal portals to other universes. No verified evidence supports that. Current physics describes them as regions where known laws break down at the center, not doorways in a sci-fi sense. Finally, the practical takeaway: the odds of a wandering black hole encountering Earth closely are vanishingly small, and astronomers can often spot big predators long before they reach us by watching how they tug on or light up nearby gas and stars. If something massive were heading our way, changes in planetary orbits and brightening of nearby gas would give warnings. So while the cinematic idea of a sudden cosmic snack makes for good drama, real encounters play out as predictable gravitational interactions, slow, strange, and scientifically fascinating rather than instant doom with dramatic sound effects. So, to wrap up, stars are born from clouds of gas, shine by turning fuel into light, and when that fuel runs out the balance tips, smaller stars fade like embers, bigger ones implode and can explode in a supernova, and the heaviest can collapse into a black hole, a place with gravity so strong that even light can't escape. Think of a campfire: low flames leave glowing coals, a sudden flare can blow sparks everywhere, and the heaviest log can crush down into a tiny, super-dense lump. Black holes aren't space vacuums gobbling everything at once, they're more like super-heavy anchors in space that really demand respect, and are excellent at hide-and-seek. If this journey from gas cloud to blackout sparked your curiosity, hit like and subscribe so you don't miss what's next. Tell me in the comments which part surprised you most or what you want explained with another everyday example. First, read them all. Soon we'll take a closer look at how we spot black holes, how do you photograph something that hides its light, and why their collisions send ripples across the universe, and yes, we'll keep the metaphors and jokes coming. Thanks for watching, and see you in the next episode as we chase the shadows of the cosmos.